Okay. Now, last class we started discussing two-port networks. So this is we are going to move on to a slightly new class of new section of topics. So before we move on, I just wanted to find out if any of you have any questions on what we have been covering previously so far. Any particular questions, any doubts on everything we have covered so far? Okay, good. That means I'm a great teacher. Huh? Okay. Or you're a great student, right? Okay. So last class we started looking at a class of networks called two-port networks. Okay. So primarily what we have been looking so far, we started off looking at basic elements, then we moved on to more complex connections of these elements, right? We looked at two-terminal elements such as resistors, capacitors, inductors, voltage sources, current sources. We looked at four-terminal elements such as what? Mutual inductors, control sources, right? And then we made more complex interconnections out of these, and just a couple of classes ago we found out how to represent complex networks across one pair of terminals, right? So we were basically taking off, we took any network N and we learned how you can replace these using, if this network has certain characteristics, right? So far we know if it contains resistors, independent voltage and current sources, and control sources as well. We know how to represent these things in a very simple way. You can either use the Thevenin equivalent or the Norton equivalent, right? Either the Thevenin equivalent or the Norton equivalent helped us describe these kinds of networks as well as you would want to. Okay? Basically, you can replace any of these. You have a question? Yes.
Tell us about how to find the Thevenin resistance again if there's a control source.
Okay. So suppose I have any network N, right? This consists of R's and controlled sources. What I am going to do, I am going to pull out all the voltage and current sources outside. Okay, so I'll call them V's and I's. I want to find out the Thevenin equivalent of this network across any two pair of terminals 1, 1 prime. What does the Thevenin equivalent consist of? It consists of a series combination of a voltage source and a resistance. What is the value of the voltage source? What is V Thevenin defined as? It is defined as the open circuit voltage across 1 and 1 prime. Okay, this is defined as the open circuit voltage across these two terminals. If I want to find out the Thevenin resistance, what do? I define this as some looking in resistance as the effective resistance between 1 and 1 prime when, so I'll between 1 prime, but in a very special condition, when N is nulled. So when I say N is nulled, so all of these voltage and current sources, independent voltage and current sources, are set to 0. What happens when you set an independent voltage source to 0? You short circuit its two terminals. What happens when you set an independent current source to 0? You open circuit those two terminals. Okay. Then what you have a network consisting of just resistors and some control sources. Now you need to find out the Thevenin resistance between some two terminals 1 and 1 prime. So I take this network N, this is null. What I am going to do, I am going to apply a test voltage V test. Okay, I am going to find out the current drawn by this test voltage. I'll call that I test. Okay, there's some magic going on here. I take these two terminals, okay, of the nulled network. I apply a test voltage. Okay, when I apply this test voltage to the network will draw some current, right? I'll call that the test current, and the effective resistance is nothing but V test over I test. This will be valid for any network of resistors and control sources. Okay. If you just had a network of resistors alone, okay, maybe a certain class of networks you can probably reduce it to a single resistor between these two terminals 1 1 prime. Okay. Right? If this did not have any control sources, if it had only resistors and some networks, you can easily reduce it using, well-known relations that you know of, combining resistors in series and resistors in parallel. You can probably reduce the network. But when you have control sources, you cannot do that. So you have to apply this technique. Okay, you apply a voltage and measure the current. V by I gives you the resistance. Or you apply a current and measure the voltage. Okay, V by I will give you the resistance. Either of these two techniques is okay. And obviously the minute you apply V test, all the control sources inside will matter, will be energized in some form. Is that clear? And of course you can have resistors, even if you have only resistors inside, there may be certain cases where it may not be easy to reduce them to just a single pair of single resistance between these two terminals. Okay, it is possible, and we will probably come across this in maybe later on in the course. It may not be easy to do it just using series parallel combinations. Is that clear to everybody? Any other questions on the Thevenin equivalent? Okay. Now, so far we have been looking at one port networks, okay, consisting of just a pair of terminals of interest inside the network. Now, it is also possible that you may very well be interested in two pairs of terminals. Okay, these are two port networks. I'll name these 1 1 prime, 2 2 prime. Okay, so now we are interested in both these pairs of ports. What kind of relationships do you expect between these pairs of ports? What are the quantities of interest? Okay, so you can have a quantity of interest which is V1, which is the input port voltage, and the output port voltage V2, input port current I1 and output port current I2. Okay, in the case of a one port network, okay, so you had V and I, right? You only had one pair of, you had a single pair of voltage current quantities, right? You just had a single voltage and a single current to deal with. Now you have two ports, so you have two pairs of voltages and two pairs of currents. Okay, how do you analyze such two port networks? So of course you can keep some quantities fixed, vary some quantities, figure out what happens. That will help you characterize this two-port network. Just like you could do the same thing for a one-port network, right? You could change V, find out what happens to I, change I, what happens to V, and that is exactly what you did here. You realize that's exactly what you did here. Okay? You applied a test voltage, you fixed the voltage, found out what the current was. That helped you find out something about the network. Okay? Now we have a two-port network, right? So you can fix certain quantities, vary certain quantities. How many such combinations are there? Assume that this network consists only of resistors and control sources. Okay, we will do the same thing we have done before. Resistors and control sources. Okay. So how many such possibilities are there? Well, let us say I can keep V1, set V1 and V2 as the independent variables, I1 and I2 as the dependent variables, characterize the dependence. Okay, you can do the reverse. Okay, or you can keep V1 and I1 as the independent variables, V2 and I2 as the dependent variables, and so on. Okay, so there are several ways of doing this. Now suppose I start off with one particular way of doing this. So let me take this network N. So for now I'll say it consists of only these kinds of okay. So for now I am going to set the voltages V1 and V2 as the independent variables and set I1 and I2 as the dependent variables. How do you characterize this behavior now? You now need to write I1 as a function of V1, V2, I2 also as a function of V1 and V2, right? So what kind of relationship do you think that these will have? It will be some kind of linear relationship. So how will you describe this? So I1 equals something times V1 plus something else times V2. Okay. So I2 will also be a linear combination of V1 and V2. Now what I'll do is I'll give certain I'll use certain expressions to denote these. I'll call this Y11, Y12, Y21 and Y22. Okay, later on in the course you'll understand why I'm using the variable Y to represent denote these expressions. Okay, I'm going to use a subscript to differentiate between these two. Okay, so the basic idea is very simple. Now you have two independent variables, two dependent variables. Okay, and each one of these dependent variables can be written as a linear combination of the independent variables. Okay, I'm denoting each of these proportionalities of constant by y with a certain subscript. So what kind of methodology am I following for the subscript? So take this particular quantity Y21. What does the 2 represent? What does the 1 represent? 2 is the current. 2 represents the port in which you are measuring the current. 1 represents the port in which you are applying the voltage. Right? But in this particular case, it doesn't matter that it's a voltage or a current. What you are saying is 2 represents the effect and 1 represents the cause. Okay? Because as you will soon see, this variable y or this term y actually captures the fact that you are applying a voltage and measuring a current. Okay? We will soon see that. So if you say there is a term Y21, okay, this represents the effect, this represents the cause. Any questions so far? What are the dimensions of Y11? Conductance, it has the dimensions of conductance. So in other words, it has units of Siemens. Okay, what about Y12? Also the same. So all of these have units of conductance. Okay? So now I have these two set of equations which describe the behavior of this two-port network. I can write this in matrix form. I1, I2, is nothing but this Y11, Y12, Y21, Y22 times the matrix V times the vector V1, V2. Okay? All good so far? So the way we are writing it, these are the independent variables. Okay, these are the dependent variables. Okay, and these are what are called the Y parameters. Okay, these are called the Y parameters of the network. Okay, how do you figure out, if I give you any specific network or any network for that matter consisting of linear resistors and linear control sources, how would you figure out the Y parameters of the network? By applying a known voltage and calculating them out. But let's look at these expressions that we have written down. Okay, so look particularly at these relations. What is the easiest way of finding out Y11, Y12, Y21, Y22? Correct. So if I set V2 to be 0, okay, and look at these two currents I1 and I2, I'll get Y11 and Y21. Okay, I set V1 to 0, okay, I get Y12 and Y22. What does it mean when I say I am setting V1 to 0 or V2 to 0? I short circuit that particular port. So now we can write down the definitions of Y11. Okay, Y11 is I1 by V1 when V2 equal to 0. Y12, okay, is nothing but I1 by V2 when V1 is set to 0. Y21 is I2 by V1 when V2 is set to 0, and Y22 is I2 by V2 when V1 is set to 0. Okay, so when I say V1 or V2 is 0, short circuit ports 1 or 2 respectively. So that's why Y parameters are also sometimes called the short circuit parameters of the network. Okay, these are also called the short circuit parameters of the network. Any questions so far? Suppose I take this example network. Okay. Can you find out the Y parameters of this network? Yes, it's quite straightforward. Okay, so what I'm going to do, so V1, V2, I1 and I2 are the variables of interest. So the first case, I'm going to short circuit the second port. I'm going to apply some V1. Okay, and I want to find out what the I1 current is and what the I2 current is. This is I2, this is I1. Note the directions of the currents, because the way it is, the directions of the currents are assumed for the two port. Okay, so note very importantly, I1 and I2 are assumed to be entering the two port network. Okay, that is the direction of representation. The actual current may be coming out, you may get a negative number or a positive number. Okay, but note the current directions. Okay, so now tell me what Y11 is. Y11 was defined as I1 by V1 when V2 was 0. Okay, I have set V2 to 0 in this particular figure. What is this? R1 R2 by R1 plus R2. But that is not Y11, it is the inverse of that. So it is often easier to use the conductances when you are dealing with Y parameters. Okay, so the Y11 is nothing but the parallel combination of R1 and R2. Okay, and that is nothing but G1 plus G2. And this particular configuration also gives you Y21. Okay, to get Y21, first of all note that the current direction is opposite of what will actually flow in the network, so you'll get a negative sign. Okay, what is this current I2? It's minus G2 times V1. Okay, it's minus G2 times V1. So Y21 is nothing but minus G2. Right? I am applying a voltage V1 here. The current flowing through R2, okay, in that direction is G2 times V2. In the opposite direction, okay, it is minus G2 times V2, and therefore Y21 is nothing but minus G2. Okay, to calculate the other set of parameters, I am going to short circuit the input, set V1 to be 0, and I have I2 and I have I1 flowing in this direction. R1, R2, R3. What is Y12? Minus G2 again. Okay, because you are applying a voltage V2 here, the current flowing through R2 is going to be G2 times V2, but in the direction of interest, okay, it is minus G2 times V2. What is Y22? G2 plus G3. Okay, this is just an example. If you are given any network, you should be able to find out the Y parameters by short circuiting the appropriate terminals and finding out the current. Is that clear? We just did this for a simple 3 resistor network. You should be able to do this for any arbitrary network, because all you are doing is you are taking a network filled with resistors and control sources. You are solving for the voltages and currents in some form. Okay, in this particular case you are applying voltages and finding out the currents. Now the main point of finding out these Y parameters, right? What do you think is the main point of finding out these Y parameters for any two-port network? Why do we want to find out the two-port Y parameters?
Well, we can figure out any currents based on what voltage is.
Any currents where?
Currents in the ports of interest.
In the ports of interest. Okay, that is kind of right. So why did we want to write down the Thevenin or Norton equivalent across one pair of ports for any network?
Simplify the job of finding out.
Exactly, right? The Thevenin or not, you could take any network, okay, and you could calculate the Thevenin equivalent and the Norton equivalent, or the Thevenin voltage and resistance, or the Norton current and resistance across any two pairs of terminals, and use this as a representation of the network across those two pairs of across that pair of terminals, okay, for a one-port network. Similarly, for a two-port network, for any complex network, we want to reduce it to these 4 sets of parameters. Okay, these Y parameters, Y11, Y12, Y21, Y22 will help you reduce any complex network across a pair of terminals, okay, across a pair of ports, okay, into just 4 parameters, into just 4 Y parameters. Is that clear? You don't need to know what is there inside the network. That is the whole point. So you can figure out whatever voltage you apply, voltage or currents you apply, you can figure out what will happen, right? You can figure out what will happen outside the network. Okay, obviously inside the network there may be many things going on, but what will have outside the network, you can figure it out very easily. Why are we dealing with just 2 ports? I started off assuming N is a 2-port. What about 3 ports or 4 ports? What will happen?
3 by 3.
Exactly. If I choose 3 pairs of ports, okay, I will get a 3 by 3 Y parameter matrix. Okay, I will have 3 pairs of voltages and currents. I can represent the equation, okay, the dependence between them as I1, I2, I3 now. I'll get a 3 by 3 matrix here, and I'll have V1, V2, V3. Okay, if I choose an N port, okay, if I choose N ports, okay, for the network, I'll get an N by N matrix representing the network. Is that clear? Any questions? Now, as it so happens, okay, 2 ports are typically the most commonly encountered kind of representation you will see. Okay, this is because most systems, okay, most electrical and electronic systems that you will encounter in the future, okay, will tend to have an input and an output, right? Typically, any system you take up, you will apply something and you will get something, right? So that is why the 2-port representation is very useful. Of course, there will always be cases where you apply something and you are interested in 2 different things. Then a 3-port representation is useful. Okay, but in many simple cases, if you look at a simple amplifier, right? You have a microphone and an amplifier, right? You have something which is converting your voice to an electrical signal, and it's amplifying it. Okay, it's making it larger. So you have an input, you want to make it larger. Okay, and then you convert it to sound again through the loudspeaker. Okay, but that is a simple case of a 2-port system. Now you also note that for this particular network that we have chosen, okay, look at Y21, that was minus G2, Y12 was also minus G2. Why is that? Y12 was equal to Y21. Why do you think that is? Yes, I think I heard the answer somewhere here. No, it's not symmetric. It's not symmetric, right? You have R1, R2, R3. The network is not symmetric by any means. Reciprocity, right? We have seen that purely resistive networks are reciprocal in nature. Okay? So, you should have already expected this. So, this is just a restatement of the same. Okay? So, this should have been expected. Okay? Now, of course, if you start adding control sources, it may not be reciprocal anymore. Okay? But if you just take a network of linear resistors, you should expect Y12 to be equal to Y21. Okay? Now, suppose I want to plot this dependence. How do I do this? Okay, suppose I want to plot the dependence for a one-port network. How do I do this? I have a one-port network, 1 prime. Okay, it consists of resistors and control sources. Okay, this is V and this is I. I want to plot I versus V. What will this look like? Straight line passing through the origin. Anybody else? Any other ideas? Huh? If only resistors, straight line passing through the origin. What if it contains resistors and control sources? So he's right. So if it contains only resistors, you should get a straight line passing through the origin. It's a purely linear network. If you have if you have control sources, what will you get? Huh? You will still get a straight line passing through the origin. Okay? Now, suppose the network also contained independent sources, what will you get? Huh? Still a straight line? Are you sure? Okay, you'll get a straight line not passing through the origin. Why is that? Can you think of why that is? Huh? Because it's not linear, okay. Huh? No. Huh? Superposition. Okay. You have learned that any network can be represented by a Thevenin equivalent. Okay. If you try to plot this series combination of VTH plus RTH, the voltage current relationship, what do you think you will get? You will get a straight line not passing through the origin. Right? You should have expected this again. Okay, if you had no independent sources, you will just have R Thevenin. Right? That represents the network perfectly. Okay? And that would have been a straight line passing through the origin with slope R Thevenin. Okay? Now if you have VTH and RTH, what will you get? What kind of straight line will you get? Intercept? Will it have an intercept VTH or what? What will be the y-intercept? Yes, so what is the y-intercept? Huh? VTH by RTH. Is it VTH by RTH or minus VTH by RTH or the y-intercept? Huh? How many of you think it's VTH by RTH? Okay. How many of you think it's minus VTH by RTH? What about the others? This is a simple series combination of a voltage source and a resistor, right? So what should it be? You can just write down the equation. Can you please do it and tell me what the exact value is? Whether it's VTH by RTH or minus VTH by RTH. Just write down the expression between V and I. Okay. This is I. Okay, you apply V and I and you want to find out the characteristics. Oh, sorry. First of all, okay, that's a DC source. What is it? Minus VTH by RTH. That is the y-intercept. And the slope is? What is the slope? 1 over RTH. You are plotting I versus V. Okay, the slope is 1 over RTH. Okay, so if you take a network consisting of these kinds of sources, you will get a straight line. Okay, and this describes the voltage current relationship. Now I want to represent a two-port network using a certain set of plots. Okay, I want to take some arbitrary two-port network. How do I do that? What kind of representation can I use? What kind of plots can I draw? A surface plot. So I will get two surface plots, right? Two 3D plots, one for I1 and one for I2. Okay, but how do I represent them on paper? I can't draw it on the paper, right? So what will I do? You must have done this before. I have I1 equals y11 V1 plus y12 V2, right? I want to draw, on a 2D graph, I want to draw this. How do I do this? I take this expression. Okay. How many ways of drawing this are there? So let us say I draw it as I1 versus V1. This is a 2D plot. I only have two axes. What kind of plot can I draw? I'll get a family of straight lines, right? I'll get a family of straight lines. Okay. I'll get a whole bunch of them for different values of V2. Okay, I get V2A, V2B, V2C and so on. Okay, I'll get a whole family of plots and one of them may be V2B equal to 0. Okay, so let's say this was V2 equal to 0 will pass through the origin. Okay, the other ones you will get a whole family of curves. You can do the same thing. If you plot I1 versus V2, you'll get a whole family of curves for V1, right? You'll get 4 such curves. Okay, that is a way to represent. And you will find that when you go to more complex networks, for example, in the next analog circuits course, you will be looking at even non-linear two ports, okay, where you can draw these kinds of curves. Okay, so you better understand this pretty well because you are going to be using this in the future. Okay, so because it is very useful to draw these plots, I1 versus V1, I1 as a function of V2 for different values of V1 and so on. Okay, so understand how to draw these. In this particular case, the relationship is linear because we are considering those class of networks in this course. You can also do the same thing for nonlinear networks also. Any questions so far? Okay. Now, we decided to choose V1 and V2 as the independent variables and I1 and I2 as the dependent variables. You could also choose the opposite way of representing the network. Okay, so if you chose I1 and I2 as the independent variables, what kind of equations can you write describing the system? So first of all, you have this two-port network. Okay. So I have I1, I2. How will you represent this two-port network? V1 is a linear combination of I1 and I2. So I'll write that as Z11 I1 plus Z12 I2. V2 is Z21 I1 plus Z22 I2. Okay. What are the units of Z? Units of resistance. So we'll say ohms. Okay. You can write this in matrix form. The V matrix is the Z matrix times the I matrix. Okay, I leave that to you. So how will you figure out what Z11, Z12, Z21, Z22 are? If you want to find out Z11, for example, Z11 can be defined as, okay, so Z11 can be defined as V1 by I1 when I2 is 0 and so on. Okay, you can do it for the other parameters. Very clearly you will have to set I1 and I2 equal to 0. What do you do when you set I1 and I2 equal to 0? You open circuit the corresponding ports. Okay, so these are also called the, so these are Z parameters or open circuit parameters. Okay. And as a homework, you find out the Z parameters for this network. Okay, actually I won't define these. I'll call this 1, 1 prime, 2, 2 prime. For the same network, I want you to find out the Z parameters as a homework. Now, what do you think will be the relationship between the Z parameters and the Y parameters? Take Z11 and Y11. What do you think the relationship will be between them? Huh? Or how do you figure out the relationship between them? Yes? How do you figure out the relationship between the Z parameters and the Y parameters? Take the inverse of the matrix. Okay, so if you represented these equations in matrix form, for the Y parameters you have I equals Y times V. Okay, for the Z parameters you have P equals Z times I. Okay, so the Y and Z parameters are simply the inverse of each other. Okay, so you can find out, once you know the Z parameters of a network, you can find out the Y parameters of the same network simply by inverting the matrix and vice versa. Okay, you know the Y parameters, you can find out the Z parameters by inverting the Z matrix. Okay, and very clearly there will be if you just take 4 random parameters Z11, Z12, Z21, Z22, you can find out Y11 in terms of the Z parameters, Y12 in terms of Z parameters and so on. It will not be a simple relationship such as if you try to write this is wrong. Okay, it will not be a simple relationship like this. because the conditions under which Z11 and Y11 are evaluated are totally different. In one case you are short circuiting a pair of ports, in the other case you are short circuiting a pair of terminals, in the other case you are open circuiting a pair of terminals. The relationship will not be as simple as this. You can go ahead and evaluate what that will look like. Any questions on Y and Z parameters? Okay, in 2 minutes, okay, I'll just tell you that for the first set of cases we took I1, I2 as the independent variables and V1, V2 as the dependent variables, that is for the Y parameters. For the Z parameters, I took I1 and I2 as the independent I1 and I2 as the independent variables and V1 and V2 as the dependent variables. Now, I don't necessarily have to choose just the pair of voltages or a pair of currents. I can choose V1 and I1 versus V2 and I2. I can choose V1 and I2 versus V2 and I1. I can choose, actually there are several combinations. How many combinations can you think of? That will tell you how many actually ports you can get. How many? 6. Okay, you can get 6 sets of parameters from this particular, for any 2-port network. Okay, the 4 most common ones are the Y parameters, the Z parameters. Okay, you also have what are called the, I'll just write this down in this way, V1 and I2, okay, is okay V2 and I1, okay. What are the units of, sorry, the other way around, I1 and V2, what are the units of H? Give me a second, I'll move to the next page, be easier to write this. What are the units of H11? Resistance. What are the units of H12? Dimensionless. What are the units of H21? H22? Siemens. Okay, so these are what are called hybrid parameters. Okay, or H parameters. Okay, similarly you can write down the other pair, okay, which would be I1 V2 is something times V1 I2, okay, and as it so turns out, G11, G12, G21 and G22, okay, and these are termed as the inverse hybrid parameters. Or G parameters, okay, but these are all simply ways of representing the same network. And you also have the other 2 kinds, which we will not explore at this time, but these are all different ways of representing the same network, and these are all useful in different situations depending on the kind of network you have inside. Many of these could be useful, but they are all perfectly equivalent. Okay, once you know any one of these sets of parameters, you can figure out what the other parameters are. Is that clear? Okay, so we'll stop here and continue in on Tuesday's class.